Good evening. So last time we were talking about some. Well, actually, we did a problem related to some factorization, and at the end, there was a situation that the things are getting a little bit out of hand because what we got. Let me say a bit. So what we got by the end was a code like this, where we had some functions and we had some variables which were in global scope. So we have clearly defined it as a bad design decision. So, but it is there, right? So what is exactly bad about this? Well, we have some, first of all, they are global. Okay, global variables are always a bad design choice. But the second, we have these functions, get vectors, add vector, and they are supposed to work with these variables. And we have the feeling that what if we somehow lose them? I don't know, something like that. So today we're going to talk about the object-oriented programming in C++, and especially we're going to talk a little bit about some misconceptions or some things that usually people get wrong, how to do it right somehow. So first of all, the first thing about object-oriented programming is actually the abstraction. Well, saying abstraction, we usually mean that there are some details which are not important, so said, and we need just to omit them. So while building the object, we need to take only the important parts. Well, what is an object? Actually, in object-oriented programming, we think that the world can be modeled as a collection of objects that are interacting, like real-world objects. But when we model, we bring in those real-life objects into some kind of C++ space. In that space, an object is actually created based on some class. A class can be considered as a recipe which defines how to create objects. So depending on the problem, we can have different visions of the same concept, same object. For example, if we think about some elections management software, imagine there is such a software, then a person, an object represented by this class, would have some name, some age, and probably some social security number that would identify, or some other type of identification number, like a passport number or something like that. So a person, it's not important how many children does someone have or what is the profession, because we are just talking about elections. But if we do another type of human-related system where we have a patient, which is also a person, right, actually? Well, the patient is going to have age and name, of course, but we also need the weight, height, blood type, some heart rate information, some recent measurements, some medical record number is going to be there to identify the patient. So this is still kind of a person, but from a very other different perspective, because now we are building another system. So for every system, every object needs to be reconsidered, and the abstraction, the process of abstraction is literally what you want to keep, okay, what you want to have about that object in your program, and what is not important, so you just throw them away. To do a good abstraction, actually, one also needs to do the object-oriented analysis and design phase. So in that phase, we must understand what objects are actually there and how do they interact, or what are the relationships between them. For example, a person can vote, right? So a voting is also probably an object in this system where we have this elections management, and probably we need to somehow make these objects interact. So that kind of things are being handled in the object-oriented analysis and design phase. And that is, in fact, even more important than the object-oriented programming itself. Okay, so OOA, OOD, and only after that OOP. After you have understanding, you have the design. So abstraction is the first phase, and it helps us to clarify what objects we are going to have and what properties or fields or functionalities these objects are supposed to have. So after that, we have the idea of encapsulation. So usually this is one of those pieces where people get a little bit confused or get it wrong. So encapsulation actually solves the problem that we had with this vectorization code. In this code, this variable can be, well, we don't see the relationship between get vectors and this variable, but there is a relationship, right? Actually, this function literally returns that. So they are in a very tight relationship. They are, I mean, there's no way to, well, in this approach, there's no way to implement the get vectors without actually accessing the result and even the index. So it means they are coupled. And that is the idea of an encapsulation. So when encapsulating, we can use classes. Classes are really good in that job to put together things that are related. Like we know the get vectors method, now it becomes a method. It deals with the variable. Well, let's then put them together, okay, so that we have a proper way to handle both of them, like a namespace, okay? The vectorizer now becomes some kind of a namespace, which means a space where different objects or names, variables, functions, things can exist, and then you can have a good access to all of them through the namespace name. So a class name actually becomes also a namespace. Yes, of course, there are also namespaces in C++, but classes are also namespaces. So even if you, especially if you think about static fields and static methods, okay? So encapsulation, it is the process when we put things that are related together into one manageable, easier to deal with, well, object, we can say. So what we usually get wrong about encapsulation, that is, we usually confuse it with data hiding. So what is data hiding? That is just another piece of operations, right, we can perform. It is the process when we hide some implementation details. And it is done basically to be able to manage the invariants. So what is an invariant? Invariant means something that doesn't change, but we're not talking about constants, okay? We're talking about some concept, some property of the world we have modeled or the object. Again, we're not talking about constant properties, okay? So a property, for example, in our simple example with factorization was the fact that the result was a zero-terminated array. Being a null-terminated or zero-terminated array is a property of this array. So whatever operation we perform, we must always make sure that there is a null value at the end. So this is how we do that. For example, while resetting, we just put 0 at the beginning and we reset the index. While adding something, we make sure that we have a 0 after that, okay? So this is some property which we must always keep track, not to break the logic. So data hiding helps us to manage those invariants, helps us to keep the consistency of the object. In our case, well, in C++, classes allow that using the keywords like public and private to differentiate between what is accessible, like is public means it is accessible from outside. They are part of the interface. So if we have a factorizer object, then we can access the getVectors method, give the number and get the result, okay? So this is somehow the the contract, the interface. But at the same time, using private, now we can hide whatever is important to keep consistent, important to manage ourselves, okay? So that's this kind of internal thing. We don't want everyone to get into details and break something. So that's why we hide the result and hide the index, and we also hide the reset and add factors methods because, well, no one from outside wants to know even that you have anything like that. So data hiding helps us to hide what is not supposed to be visible because it is dangerous. It can bring to the leak or breakage of invariance. Okay, invariance cannot be kept anymore. So these three steps together, abstraction, encapsulation, and data hiding, gives us some understanding that the world consists of objects. We can design the system which manipulates the real world, right? Based on these objects, we need to define classes, properly put things that are related into that class, forget about irrelevant things, and then also make sure that whatever is important to be properly managed, not to be broken or corrupted, okay? So we must hide them. So these several steps are so natural, like usually we just do it along the way. I mean, just while coding, we usually put every data member into the private section. Usually we don't want everyone to know that we have anything like this. And but sometimes, on the other hand, we think that, oh, I need to provide some access, right? Somehow people need to get some, like, well, if you can recall, so we have a person, right? And the person has a name. Obviously, that name must be somehow populated, right? Someone will have the need to know the name of the person, like to print at least in the list. So yeah, it must be also accessible. And in that case, we can have accessors, a method that can give access. If you want to get, it will return you the name. And if you want the age, okay, you can have another accessor for the age. But there are no set accessors. So there is no way to set the name, or only while constructing the object. Okay, so the objects, while created in this particular example, they cannot be modified. And data hiding helps us to implement that. Okay, so we can make sure that after we create an object of person, it will never get changed. Unfortunately, C++ is a very powerful language. So in C++, you can do things that no one would love you to be able to do. I mean, if I have a class and I have some encapsulation, I have data hiding, etc., then I don't want you to come and change whatever objects are supposed to be kind of constant, right? But in C++, you can have a pointer which can be casted, and then you can do some pointer arithmetics, and you can get access to the age field, and you can change it, even if it is private. I mean, in C++, many things are possible, but not recommended to do. And when you start doing them, probably you will even break some recommendations or even some restrictions that are in the standard. You will get into some undefined behavior field, okay? The undefined behavior means you don't know what will happen. I mean, if you try doing that kind of manipulation, try take the pointer, cast it, do some arithmetics and calculate the address of an age and try to change it directly, yeah, there's a chance it will work, but there's also a chance that it will break something else because there's no guarantee how exactly the objects are laid in memory, laid out. So you can actually just change something else, and it can probably break your program logic, and it will just bring to some crashes later. So the idea is the following. If something is hidden, there is a reason behind that, okay? The data hiding thing is there to keep the objects consistent. Don't break it. Yes, of course you can, but just let's keep that contract. Okay, if it is hidden, just don't change it. Of course, it's not fully properly hidden because even the header file of the class contains all the private fields in it. I mean, if you just include a file, it means you have access to that file. You can just go open it and see that there are these private fields, and you can understand their address layouts, okay? And you can do bad things. But yes, of course, you can. I mean, that is your program, that is kind of your memory. You can break it. Just let's keep consistent with that, okay? If it is private, just don't break it. Okay. So let's move forward. The last two pieces are a little bit more complex, more they need more time and effort. So let's see. The next one is called inheritance. So inheritance is the following. Imagine we have a situation when we see that two objects are so close that we can even say that one of them is actually an instance of the other type. Okay, let's say we have A and B, and we can say that B is an A. For example, we have animals and we have horses. We can say that horse is an animal, right? So, I mean, it's so natural that the structure of that sentence is so true, right? The horse is an animal. So the fact that horse is an animal can lead us to the following situation in C++, where if we have a class which represents animals and we have another class which represents horses, then we can say that a horse is an animal, like this. So this is called public inheritance. There are several more types of inheritance, like protected or private or even virtual inheritance in C++, which is a very a powerful tool set. So usually you don't need all of them in every project, and usually public inheritance is just what you need. Let's say in C#, I believe there is only public inheritance. You cannot have all these other things. So in C++, you have many other options. So that is another topic by itself, all those different kinds of inheritance and which of those are more or better applicable for some particular situation. So anyway, this is the situation with classes A and B. Imagine B is an A. Okay, so this is true that B is an A. That's why we can do that inheritance thing. And after that, what we know is the following. Anything that is not private in class A, so it can be protected or it can be public, they are accessible also in B. So in B, I can actually access X. I mean, I can say these X equals 1, for example, right? I can do that because X is inherited from A. X is here, so I have it also in B. Very convenient. I mean, from the programmer's perspective who deals with C++ code, it's very convenient. But then things get complicated when we want to do different things between these types, okay, objects of these types. So let's see, why is it like that? For that, we are going to do a little deeper investigation, okay? Because on the level of C++, this is all we have. I mean, the standard tells us that, yes, B has everything that A has that are not private. That's all. So you can just access them. Yeah, but how? How does that even happen? For that, I have prepared, well, I have pre-compiled, so we can check it in the make file even. So I have done some compilation to generate the IR code, so LLVM IR code, which is a helper mechanism, okay? It is just there, we can use it, and here it is. So our inheritance C++ file is compiled, and it is, well, transformed to another form. So this form is not very usual for programmers to deal with, but there are people who deal with it. I mean, it is so natural for some kind of professions like compiler developers or high performance computing engineers or some system engineers in general. Okay, so sometimes you need just to go deeper than the C++ or even deeper like to the assembly languages. Okay, so IR, LLVM IR is in between. It is an intermediate representation. Okay, from one end, it is kind of a machine language, but on the other end, it has some high-level concepts. And they help us to understand. Okay, you don't need to know the language itself to understand what I'm trying to communicate right now, but anyway, you must understand some basic things. So first of all, we must understand that whatever we have in C++ code, they must have their analogy, okay, some translation in the LLVMIR code. Because later they are going to be translated to assembly language and then to machine code, and the CPU will deal with them, okay? CPU will implement the program logic. So everything we have here must also be somehow translated into IR. So that's why we have class A, here it is, and we have class B. And what is interesting, we can actually see the structure. The structure of class A is this. There is just one I32. So it is a type, something like a struct, okay? But there is no keyword like that. It's just a type, which consists of one I32, which means 32-bit integer. This is it, X. But it has no name, so the name is just lost because the CPU doesn't deal with names. The CPU just cares about addresses. So that's why we don't have the names on this level, okay? We just have types. Okay, the class A consists of one integer. What about class B? Class B literally consists of class A and another float. So this is that float, it is the Y. But it also clearly states that class A is embedded. It exists within class B, which is strange because those who know object-oriented programming and object-oriented design, you probably have heard about composition, right? So there is inheritance and there is composition. Composition would mean when you put one object into another, like we could somehow put A, an instance of A, into B as a field. And sometimes there's a recommendation to eliminate that tightly coupling which the inheritance brings in. So when you declare B as a child class of A, you really couple those two classes heavily. I mean, whatever gets changed in A, it affects B, which is sometimes something that you don't want because maybe A is an external entity from some library. You don't want your code to be affected that directly. So there is the alternate way, the composition. But when you do composition, then you need to take care of all those methods that you want to delegate to that internal object. So you don't have everything that A has, okay? A is kind of on its own, and you don't magically provide all the functionality that A has outside from your class B if you do composition again. But turns out that when you do inheritance in C++, actually a composition happens. Okay, actually class B that is on the lower level, it really contains an instance of class A. And that breaks a little bit of the flow of thoughts, because you are thinking that, yeah, you have some separate classes, they somehow are related, but now you see that, oh, that's how they are related. Okay, so literally there is an instance of class A in class B. But yeah, what about other stuff? First of all, a big misconception is that methods are, so is F in class A? What does that even mean? I mean, what do you mean by saying F is a method of class A? Do we mean that it is physically in that class, whatever it means? Well, as we can see, there is nothing about F in this type. It has no methods because the CPU even doesn't know anything about A and B, but the CPU knows about functions. So we can go down and try to find, actually, I will just show you. This is F. Probably you will not recognize it as f, but let me decode it for you. So this is the so-called mangled name of the method. In C++, we know there is the function overload, a very powerful and useful tool, but that tool needs your functions to have different set of arguments, right, in order to be able to do that overloading thing. So in fact, the C++ compiler takes the name of this function f and mangles it. It builds a new name which clearly defines who this f is so that it doesn't get confused with anything else, any other f's, okay? There can be many f's. Well, actually, this says that this is a mangled C++ name. One says that we are going to have one letter after that, A, which is the name of the class. And then we have another one which says after one, so one more symbol is name, so F. If you just want, we can rename it to a function. And we will see after rebuilding. Oh, yeah, I'm sorry, we have a call here. So if I rename it to a function like func, then we will see that a little bit handling is supposed to be implemented, and here we are. So now it says 1A for func, which means that the 4 characters long is the name. And after that, we have additional symbols, and they actually encode the parameters. Well, in this case, it is empty, but we can say that, no, it's not empty, it's void. So void is a type, right? And exactly this EV tells us that there is a void parameter. So this is called a mangled name, and this is how the compiler handles function names. That's why C++ is very bad in situations like when you want to cross the boundaries, when you want a library call from your code, the library and the caller must both kind of have an agreement on the naming. So if your library is created using C++ and your caller is also a C++ code, they can do that thing because they both know how to mangle names. But if the library is written in another language, let's say in C, then there are no names like these in C because C doesn't support actually that function overloading. And in that case, your C++ compiler will not find whatever they think the name will be. So you must take care about the naming and calling convention in order to call a function outside from C++ space. Another library, it's very regular. I mean, calling something from a library. So this is the function. Then where is the class? Class name is just encoded into the function name. This A, okay, this capital letter A is the whole thing about function. We don't have anything else. I mean, any other way to understand that this function belongs to class A. But then comes the next thing. We all know that this variable, this, is magically somehow created and you can access it right from the method. Like, what does that even mean? I have nothing like this here, so why is it there? How can I use this? Here, how? Let's see. The function has a parameter, a pointer, which is called this. That's all. I mean, literally, the compiler generates a code where a variable, an argument named this is created. And in the code, in the body, this can be accessed and you can use it because it is just a regular parameter. Yeah, that's how the things are implemented, which is kind of boring when you see it. But at the same time, the question is f in class A, it becomes so irrelevant. Like, no, of course it's not. It is just a function on its own. It has just a separate, a spatial parameter of that type. I don't even know its type. You see, I don't have the type information. I just know that it is a pointer. So this is just a pointer. And it is called this. So where is class A? It is here, this one letter, that's all. But how does it get this? Where does it come from? It comes from the callers. So let's see. Here I have the main function where I have an object of type A, and a dot function is called. So whenever I call a dot function, here what happens? This is it. A call. So this is an instruction for that LLVM machine. And in call, I have this function name. And as a parameter, I provide a, which is it is an object of class A. I mean, it is just a pointer to an object of class A. In fact, it is a pointer. So this is a pointer to A, and we give it as a parameter while calling the method, which is just a function. I mean, it's not a method anymore. It's just a function here. And that's how it happens. If I wanted to call function for B, then I just pass B to that function as a parameter. Okay? And even for G, same thing here, same exact thing here it is. For G, this is G, and this is another parameter for G. So functions are on their own. They live in global space. By the way, they are global. This at in the beginning says that they are global names. They can be accessed from outside, from other modules, other C++ source files. You can call these functions. But the compiler will only allow you to call if you call them using some object, okay, and call them as a method. That is the rule. So the C++ compiler makes sure that whoever tries to call, they follow this syntax. That's it. If you follow this syntax, then it is a public function, so you can call it, no problem. And what is important, they are not within classes, whatever it means, okay? They are just in the global space. Now we come to the next question, which is also very confusing when we have inheritance. Sometimes we want to use some object of child type in some context where it is necessary to have an object of parent type, or the opposite is also true, right? So sometimes we have the opposite situation. I mean, we just want to use. So let's see. First of all, we cannot call a.g because class A has no g. Okay, it's so obvious. But for B, we can call both. That's very obvious. Now, what will happen if I try to assign B to A? So B is the child. What will happen? If you check that this thing, so the classes, the types that actually implement those classes, then we see that B contains an A, and it is even more than A. So when we do this assignment, then from the compiler's perspective, what we are just doing, we are just taking part of B, okay, and copying it to A. Just part of it, the first part. I mean, it's a safe operation. Instead of the whole object, I take part of it. It's a safe operation. I don't cross any boundaries. I don't go to other objects' memory, okay? This is just my memory shrunk a little bit. I want part of it. And literally, memcopy is called. I mean, if you know what I mean, okay, this is literally memcopy. It is an intrinsic. In this case, it can be translated to anything. Well, it can be implemented in different ways, but anyway, it just says take B, take A. The first one is the destination. So copy B to A. Well, how many bytes? 4 bytes. Why? Because there is just one integer in class A. That's it. Okay, so actually this assignment, which you probably know that you can overload, yeah, you can re-implement somehow, the compiler will generate an assignment operation for you for any class, like for free, and it will just copy. And in this case, if you assign objects of different types, the compiler just makes sure that B is copied in terms of first 4 bytes. That's it, not everything. It is safe because we can clearly see that the first 4 bytes of B is an instance of A. I mean, semantically, it is a properly defined operation. Everything matches. But on the other hand, if you try to assign A to B, then there is a big question because A is less than B, right? So if you copy that part, okay, let's see what the compiler thinks about it. So it just says that there is no such an operator. I mean, from the compiler's perspective, you are trying to do an unsafe thing because B is already there, B contains its own fields, and then you want to copy whatever is in B into A. Sorry, I'm really sorry. Whatever is in A into B. So what is in A? Well, it is not the whole B, right? So we have something that B, so after this operation, if you are not careful enough, you just copy in the same way, like you do just mem copy whatever is in A into B. Then what about the rest of B? So what will happen to this poor field? I mean, Y is not assigned. So you will have inconsistency because you will have an integer that is properly assigned and a float which I don't know what it now contains. Okay, so this is an inconsistency. The object becomes partially initialized. That's why the compiler just says that there is no such an operation. So the compiler will not do that for you because it is dangerous, because as a result, you are going to have a non-consistent object. But if you want, of course, you can define this operation. You can go and define it, and then you are the owner of the situation. Okay, after that, it's your problem. If something goes wrong, the compiler is kind of on the safe side. Okay, from compiler's perspective, it is not natural to do, so there's no operation for that. But on the other hand, when we assign B to A, we think that B is larger than A. How could we put a whole object of B into small space of A? Well, actually, we don't. This is what happens. We just copy the first 4 bytes, not the whole object. So anytime you want to use the child class object as a parent class object, you just shrink it and use the first initial part of it, which is literally of the correct type. So this understanding of how the objects are really implemented changed a lot for me. That's why I'm sharing this knowledge with you, because I hope you will also find something useful in it. So we will discuss the questions later. Let's move to the next step. Next step in our story, it is the polymorphism, which is another big deal. And actually, it is the hardest thing about object-oriented programming. And that is the most powerful tool we have. Actually, it uses inheritance and it brings in even more. So let's see. Polymorphism, it is when you have a single interface and multiple implementations. What does that mean? There is no specific word for interface in C++. So saying interface in C++, we actually mean something that we can call from outside, something that we can use from outside of the class, let's say. But in case of polymorphism, in C++, they say that there are 2 types of polymorphisms, like there is a static polymorphism and dynamic polymorphism. So static is the one which is related to function and operator overloading, okay? It's not about object-oriented programming. It is just a feature that is there, you can use it. So we are talking about the polymorphism in object-oriented programming, which is the dynamic polymorphism. So it means, by saying dynamic, we mean that the compiler doesn't know everything at the moment of compilation. It must be handled somehow dynamically while the program is being executed. While the function overload thing, the compiler knows everything. So just the compiler will check the names and emit the calls for you. Okay? So dynamic and object-oriented polymorphism is the following. We have a class A and we have B as it was earlier. So B is an A. The only difference is this. We have this word virtual. So if we define a function as a method as virtual, it means that we probably want to do some dynamic resolve of the real function being called. What does that mean? So in this situation, we need to do the following. We declare f as virtual in the parent class. Then in the child class, we do an override. So override and overload are completely different things, okay? They are very close. It is so easy to get confused. So overloading, when you have the same name, different arguments. Override ensures that the name and the arguments are exactly the same, okay? You can override only when you have exactly the same arguments. If I add another one, then overriding will not work anymore. So the compiler makes sure that it is exactly the same method that you are overriding. Now, to override means the following. In child class, you understand that whatever is implemented in the base class is wrong for you. It doesn't properly work for you. Okay, maybe you have another steps to perform in order to get the job done. So you override the method implementation in the child class and you implement it in your way. Let's call it your way, okay? The child class has its own implementation. So this is a good idea, and as long as we know how to use it and where to use it. So where to use it? Well, usually if you have collections of objects, or if you have some big systems where you don't really care about all those details of child classes, etc., we can say that child classes are kind of an implementation detail, and we don't even want to know sometimes, okay? So in those cases, we just deal with every object as their base class objects, because we don't care about any details. Like in this particular example, class B has some additional protected field, and maybe it can provide some additional, I don't know, a method that will do some interesting things for us, right? But we are not interested. In that case, we just treat every class, every object from that hierarchy as a parent object. But then turns out that every object has its own implementation of f, right? And probably we would love to be kind of aware of how exactly they are implemented without getting, we don't want to know how exactly they are implemented. We want to use that implementation because class B knows better how to call f, okay? What to do when f is called. So in that case, we must use this polymorphic behavior. And how in C++, when you want to have that polymorphic behavior, there are a couple of things you must take care of. To get there, I will just do another make. So I have prepared polymorph IR target here, which generates this LL file. So let's see what it means. Here I have an example. I have an object of class A, and I have a pointer which points to an object of type B, but the pointer type is A pointer. So A doesn't matter much here. It is just for demonstration. So if I call F for A, okay, it is okay. A has that implementation, right? So if I do the call, let's find it. So I have it's hard to find because we have so many things. So anyway, it is a call. Yeah, here it is. There is a call with the name of, oh, where is it? Did I regenerate? Okay, I hope we will find it soon. So it is called F, and probably we'll just search by name. So let's see its name. Somewhere here we have F. This is it. And we can just find by name. Oh, it's not being called. Sorry. For whatever reason, it's not being called. Let's go and check what we did wrong. Yeah, this is what. I'm sorry. I was just experimenting. So optimization is another big thing. You should never mess with optimizer flags and stuff like that if you want to have control over what is going on. So let's get back to it again. Here is the function, and no, still we don't have the call. Okay, believe me, the call will be there if we call it. But later, when we call it for for the pointer, so let's see what will happen in that case. Again, now I want to find that exact line, so I will just comment out everything else to have minimum code and hopefully, okay, I will comment first thing. So we need minimum code to understand what is going on here, because here we have so much of code. Yes, it is correct. So we have B again. B it contains A, as we know, and then if we go to main, this is the main function. So we have actually functions on this level, which is quite good. So this is the call to a constructor, I believe. And then we have, this is new, in fact. Then we have memset, and we have, so what strange thing we have is this. Can you see it? We have call. So we have a call, but the parameter is this. So there's no name. I mean, you cannot find a name for that function being called. This is the problem with polymorphism. So when you have a polymorphism, the compiler doesn't know which function you are going to call. Why is it like that? Because the pointer is of type A, and the whole idea of polymorphism is that I want to call exact that implementation which is related to this class. Okay, that is the runtime type. Okay, we have the static compile time type, which is A, and we have B, which is going to be dynamically decided by the runtime. Okay, whenever the program is actually being executed, because we could have a proper if statement. Like there's a chance you can have an if statement and you can make new A or new B based on something. So the compiler doesn't control whatever is going to code. That's why instead of that, the compiler just does some compiler thing. It creates code that will make sure that the proper function will be called. So this %1 is the function pointer. How do we get that? We get it from this. It is a pointer to some table where functions live, or it is a pointer within that table. How do we get this pointer? Here, we get it from a V table. That is the exact table where those function pointers live. What kind of function pointers? Well, turns out that this V table is prepared by the compiler. So again, it generates the code for V table to be there, because when you come, the compiler needs to make sure that when it is time, your code will run properly. So this V table, it is %0. Okay, it is read from %0. So who is %0? 0 is PA. Oh, now we know who is that, right? PA is our variable. So PA, the pointer, well, so it points to some location where some table lives. Turns out, I mean, we didn't even think about it like that, but turns out it is like that. So how come we didn't have any tables, right? What kind of table is it? Well, here it is. Class A, it is not that simple anymore. Let me show you. class A should contain just one long value. But instead of that, it contains a pointer and a long value. So this pointer comes literally from the fact that we have a virtual function. So if I remove these virtual things, now it's just a function, then the pointer is gone, okay? But B is also gone for whatever reason. Where is B? I don't know what happened to B. Now it is not there. Okay, anyway, the pointer is not there anymore. And if we bring it back, so having a virtual method in your class dramatically changes the class structure. So be very careful. I mean, now class A contains an extra pointer, which is kind of transparent for us. We don't see it. I mean, the pointer itself, okay? We don't see the pointer from our height of C++. We don't know anything like this would happen there, but it happens and it affects things. So first of all, it affects the layout of the object. The first field now in A, it's not a long X. I mean, think about it. If you have a pointer to A and you want to do that pointer arithmetic magic and play around and, for example, get access to the hidden field, actually it is hidden, right? And change it. In fact, you are going to change this pointer and it is going to end up very bad. Okay, so that's why it is an undefined behavior when you take the pointer to an object and try to access its fields in an illegal ways, okay? So this is just a demonstration that it will really badly affect your code, the execution of the program. But for B, well, there nothing changes because it just has an object of A and another I64, which is that Y, this one. Okay, so what we currently see is the following. In order to call, here it is, to call using the pointer, the compiler needs to generate so many levels of indirections in order to find which function you are trying to call. Well, in this case, we have just one function. That's why this index is 0. If we have two virtual functions and you want to call the second one, this index will be 1. That is the idea. It's just a table. It's an array of pointers. So what does that mean from the performance perspective? Having this kind of structure, well, you must pay for that, okay? So from the compiler perspective, it just generates the code. So the rest is not the compiler's problem. But from our perspective, when we want to run the code, so here is an example. We have a big number, n, which is like, as you can see, it is extremely big. It is long because I want to fit maybe 10 digits long, I don't know. And then I want to measure how long will it take if I call f using some pointer for n times. And then I do a similar block where I have this call, which is direct call of f, okay? I hope we can find that call here because I hope that the optimizer hasn't removed it from here. Call, yeah, here we have so many calls. It's really terrible. So because of these chrono calls, we have so many calls now, it is really hard to find our function. But it is there. It is somewhere here. Oh, here it is. I just found it. So this is the function name. As we can recognize, it has 1a, 1f. Okay, this is the function. And it is being called for object a. Here it is. A is actually not the object. It is a pointer on the right side. So here it is. We have the call, and we have the other call, the indirect way of calling. Where is that? I just want to make sure that we have both. Oh, now it is called person5. Whatever. Anyway, it is the same structure. We take it from vtable4, which is again loaded from person3. Well, person3, it is PA. Okay, same kind of code. but in other place. That's why we have other names. So we have two loops, and I want to make and run these loops. So it takes some while because we have so many of them. For the first execution, okay, let's pay attention. So for the first one, it is the virtual call, and the second one, it is direct call. So virtual call took 3.3 seconds to call so many times, millions of times, while this is, well, the direct call took 3.2 seconds almost. So the difference, well, yes, of course, there is a difference. So the difference is, well, it is 0.1 second in 3 seconds. Okay, so we can say that it is more than 1%. Okay, it's several percents of slowdown. But it is just several percents of slowdown. I mean, we have a powerful tool which can help us to define, design the system clearly, to have that polymorphic behavior, to have that freedom of using objects without getting into details how exactly they are implemented. But at the same time, we don't have a huge pay. But this is only till the moment when we turn the optimizations on. So in this example, I have just disabled the optimizations. So let's see, in makefile, I have two variants of the same code. So one is called polymorph exe, so exe, which says 0 optimizations. And there is also polymorph optim, which says optimization, like the second level of optimization. So if I try make polymorph optim and then run it again, what's called polymorph optim. So it is called polymorph optim. When I run it, the virtual call still takes 3 seconds. As you can see, 3 point something. Well, it varies, okay? You can run 10 times and take the average. But as you can see, the direct call takes really lower, much lower. I mean, if I run it several times, we will get different numbers. Sometimes this number can go really low. So what happens is actually the optimizer is so smart that it can clearly see that if you call F for A, it means you want this, right? It can just calculate what the result will be if you run it so many times. It will just put the answer there because the compiler is smart. Okay, so whenever you turn on the optimizations, things change absolutely terribly sometimes. When optimizations are on, you don't know what will happen anymore. You don't really control what can change there. But the idea is that compiler takes your source code and transforms it using some mathematical models, maybe some graphs, some theorems from other fields, etc., and then changes your code, making sure on each step that your code still does exactly the same thing, but in a different way. I mean, faster. That's the idea. So we are going to talk about optimizations in another session. It is a long story. It is about high-performance computing, and that is another topic. So for now, we have the following. A question like, how expensive is it to use polymorphism in C++, given that we have so many levels of indirect calls? Well, the answer is, it is not very costly. It is not too expensive because now, as we can see, it almost became a regular function call-like. But on the other end, the optimizer cannot optimize it for us because that will happen in runtime. So the compiler must make sure that this code will be executed, okay? And then the optimizer cannot just magically replace the code with its result. That is usually what happens when you turn on the optimizer. So it becomes a little bit more costly than the direct call, and it breaks the optimization really bad. But it gives you beautiful interface so that you can work with that. I mean, high level, high design, high quality design of your system. Does it work? Well, I think it does if you are not doing specifically high performance computing. So if your goal is high performance computing, then you must have another design goals in your head, okay? In high performance computing, the design isn't important at all. So you break all those good design recommendations, design patterns, etc., etc. You break everything to gain performance. So polymorphism is one of those things that you will probably have to break in order to get the high performance. But if you are not really into the high performance, you are not counting every tick, every CPU clock, then probably you are okay with that, and it will give you beautiful control over the design. Okay, actually, this is all that I have prepared for today. Kind of basics of object-oriented programming and what we usually get wrong about that in C++. So I will be happy to answer questions if there are. No questions. Okay, then thanks for being here today, and we will have the recording later available on YouTube, so you can revisit this. Thank you and goodbye.